Okay, so today we're going to talk about causal inference, and this is very important for your papers. This is kind of the bottom line, or that last section, what I want you to be thinking about. So we're going to have a lecture, and then we're going to have a group exercise at the end of the lecture that's going to be based on the reading that you were given. So let's talk about causal inference. So we went through this last week that, you observe an association, you want to know, is it real or is it spurious? If it's spurious, it could be bias or systematic error. We went through a lot of reasons for that last week. It could be real, but due to a third variable. If it is, we might call that confounding. If it's not due to a third variable, we want to know if it's due to chance or one of those type 1 errors. And if it's unlikely, then we can start thinking of a causal relationship. But there's a lot more to it than simply that. So what is a cause? This is a quote from Mervyn Susser, who has been on the Faculty of Epidemiology here for a while. I had the pleasure of working with him for the 3 Mile Island study. I worked with him, and he's a really bright guy and has spent a lot of time thinking about causality. So if any of you are interested in this, you could look him up and find some cool papers. But a cause is something that makes a difference. Insofar as epidemiology is a science that aims to discover the cause of health states, the search includes all determinants of health outcomes. These may be both active agents and static conditions, such as the attributes of persons and place. So why should we worry about causality? Well, one of the things is, if we determine that something is a cause of disease, we can intervene. We can go and say, let's get rid of that so that we can have less disease. The known cause also allows us to reduce or to prevent disease. And what we want to do is try and figure out, well, what are the causes of disease? What makes different distributions of disease? Why do we see more disease in certain areas or certain people as compared to others? And in the end, what we want to know is whether there's a cause and effect relationship between factor X and the development of disease, or Y. So we have gone through week by week all of the different study designs, starting with clinical observations or available data. Then we went on to case control studies, cohort studies, and then the top of the pyramid, a randomized clinical trial. Now, this is ideal in some circumstances, but as some of you have talked to me about it, you can't do it for everything. If your paper is looking at a harmful agent, you can't do a randomized controlled trial. So there's 2-step process that we use to review the evidence that we might have between a risk factor and a disease. We want to determine if there was an association between the risk and exposure and the risk of disease. We do that sometimes with group characteristics, which is ecologic studies, or individual characteristics, like a case control and a cohort study. And again, if it's a beneficial exposure, we have the option of also doing a randomized controlled trial. Then once we see an association, or we don't, once we see an association, if we don't really care, but if we see an association, we want to then say, is this a causal association or not? And these 2 steps are shown graphically here, where you look at the environmental exposure or the host characteristic, what do they eat, what we're focusing on here, and then they look at disease or other health outcomes. And you want to know, are these 2 associated? So going back to some of the earlier things that we did with ecologic studies, here we had a correlation between dietary fat, but this is per capita supply of fat calories, and the incidence rate per 100,000 women for breast cancer. So each one of these dots represents a country, with the U.S. being high in fat intake and high in the incidence of breast cancer, Japan, Hong Kong, some of these countries being much lower. So what is the problem here? We see an association, but what's the problem? Right, it's ecologic what? Right, it's a potential for ecologic fallacy. We don't know if the individuals here that got breast cancer also had the high fat intakes. We only have group data. So this is the crude incidence rates and relative risk of acute lymphocytic leukemia by a group of women based on the trimester of flu exposure for children younger than 5 years. So there was a high relative risk for children, it appears, who were in utero during a flu outbreak during the first and second trimester. If you look here, the incidence rates and relative risks are very high. 3.2 and 2.6, the incidence rates are much higher than later. So it looks like if you're exposed during these first 2 trimesters that you might be concerned. But what you don't know is how this data was collected. In essence, what they did is they looked at birth certificates and cancer registry data. They knew when there were flu outbreaks, and they just calculated, was there potential for exposure to flu? But in this case, we didn't know if the mothers of any of these children actually had the flu during their pregnancy. So it looks pretty impressive, but in reality, it's no individual data on exposure, just like the last example. So we've talked a little bit about observational studies. This would be cohort studies, case control studies, cross-sectional studies. They're cheaper. There's not ethical issues. People are doing whatever they would do normally. They're faster to conduct in some cases for the case control study. And you can test a lot of hypotheses and associations. When you do an experimental study or a randomized controlled trial, the variable that you're interested in is easy to control by you as an investigator, and other extraneous variables or confounders are readily controlled by you as well. So there are, because as we talked about last week, by doing randomization, we get rid of the confounding that could be there. So you could, in this case, give a supplement to someone and see whether or not there was a lower rate of disease. We had the micronutrient symposium this weekend, so you could think about the different trials that they talked about that were supplements being given to people. That's an experimental study. Some of the others were observational studies where they just looked at what was the usual intake. So if you're talking about observational studies like cohort or case control studies, we want to know if we look at an association. I have 2 papers on meat intake and colorectal cancer. I want to decide, is this real or is it false? Is it just spurious? And these spurious associations or findings that look like they're real can result from confounding, selection bias, a lot of the things we talked about last week. So when you find an association, one of the first things you want to do is make sure that you don't have any confounding or things that are going to interfere with your finding not being real. So we have causal associations where the characteristic under study leads to the disease. It could be that there's something else that's due to confounding, where it's not that characteristic under study leading to disease, but just like our definition of confounding, we had an association between that characteristic and factor X. So this arrow could be one direction or both directions. But factor X, we know, clearly causes disease. So that fits the definition of a confounder, and that could be why we see the association. So just as an example, it could be that you're looking at increased cholesterol and whether that leads to an increased risk of coronary heart disease. Or is it due to confounding, that the increased cholesterol is related to some factor X? It could be a genetic profile of high cholesterol that maybe independently increases the risk of coronary heart disease. So you're not really seeing this association. It's all fed through this factor X. So this is the percentage distribution by birth weight of mothers who smoke, which is shown in the dashed line here, and mothers who don't smoke, which is shown in the solid line here. So what happens to the birth weight, which is found on this scale, if you have a smoking mother? Yeah. Right, it goes down. Basically, we see the entire distribution is shifting to the left. Smokers have slightly smaller babies as compared to non-smokers. So the whole distribution basically goes from this point and shifts over to the left or to a lower birth weight here. So what is one of the major risk factors for low birth weight? Anyone have any ideas? Yes? It could be alcohol use. Yeah. It could be lower food intake. Yeah. The mother's weight, yeah. Premature birth or length of gestation. That's what I'm looking for, because that's on the next slide, so I get to move forward. Okay, so here is, again, looking at non-smokers here with the solid line, smokers with the dashed line. But what they basically did here is that they said for any length of gestation, whether it's 40 weeks, which is the average length of gestation, a non-smoker always has a higher birth weight than a smoker. And that's true even if you look at shorter lengths of gestation, like 36 weeks or whatever, you still see that non-smokers' baby's birth weight is higher than that in smokers. So in general, we can see that even at equal length of gestation, smokers have smaller babies. So that's controlling for one of the major risk factors that there are for low birth weight. And this graphic shows that there's actually a dose-response relationship. This is the percent of the population that has a low birth weight baby, or less than 2,500 grams. This first line is 4.7% of non-smokers have that. If you have less than a pack a day, you smoke, but not as much as a pack a day, it's 7.7% rates of low birth weight. And if you're more than a pack a day smoker, it goes up to 12. So what we see here is what we'd call a dose-response relationship. The more smoking, the more likely you are to have a low birth weight baby. And on the basis of this data and some others, this is pretty much considered a causal relationship. There's been a lot of studies that show it. They tried controlling for a lot of the confounders that you mentioned here in class, and they still saw the relationship. So when we think of causality, it's based on a few different things. One of the things is, what is the strength of the evidence that you're seeing? So in this example, a case control study was looking at antiperspirant use and risk of breast cancer, and it found that the odds ratio was 3.2. The confidence interval was 1.1 to 8.2. So we have a moderate strength of association, 3, 2, 3, something like that is pretty moderate in terms of the strength, and it's significant. But no one else has done a similar study. So you're thinking, well, do antiperspirants really cause breast cancer? Do I have to walk around sweating and smelling? And the answer is, you want to say, what other information do I need? What other information do you think you would want before deciding on this? Anyone have any ideas what else you would want to see? Yes? So you might want to look at confounders, things like hormone replacement therapy, make sure that result is real. Yes? A cohort study, so you might want another study, and you're going for a stronger study design too. Yes? Right, you could look for a case of dose response as well. So you got a lot of it. You want to think, was there a confounder? Is there any bias? Is there selection bias in who I chose? And then what you always need to think about is that one study typically is not sufficient, especially if it's a case control or a cohort study, to say that there's a causal relationship. You really want to also have consistency of findings, so you want more than one study. So when we're trying to figure out whether or not a relationship is causal, it's not really a simple process. One general rule is a single study. No single study is going to be sufficient to establish causal inference. And you need to have critical judgment and interpretation of whatever findings you're presenting. Now, when we did the case control study, I did show you one example of DES and cervical cancer. And that, I said, this is one example of a small case control study that the findings were so strong that they basically just took the drug off the market. But that's very rare. We don't oftentimes see something like that. So this is what we're all about today. Does the exposure of interest lead to the disease or outcome, or do they just co-occur? That would be an issue that we want to be concerned with. We're also concerned with differential misclassification or bias that we spent time talking about last week, because that can create an association between our exposure and disease, even if there is no such relationship. And with that, you can always think about the coffee drinking and pancreatic cancer example. So, or is it possible that we have this exposure of interest, and just by chance, in this one study, it led to the disease or outcome? What kind of an error would that be in terms of statistics? It was on your exam. Most of you got it right. Type 1 error, okay? So, and we allow for this to occur about 5% of the time. We're willing to take that chance. Then we want to think about, we have this exposure, we have this disease. Is it really some confounder, one that we collected the data on and we can do analysis and try and control for it and see if this relationship goes away? Or is there a confounder we forgot to collect? And we're concerned about whether this association is maybe just due to the presence of this confounder. And that's why we always want to do some of the control methods we talked about last week for confounding to get rid of that. When we also think about causality, we're thinking about, well, what's the pathway? Is it a direct association where you have a factor and it directly causes the disease and there's no intermediate steps? But you can also have an indirect association and have it still be causal, where a factor causes a disease, but only through an intermediate step or steps. And that's just graphically shown here, where direct is the factor leads directly to the disease, or indirect is something like this. Maybe this is carcinogenesis. So you have something that starts the initiation of a cancer, but then you need other things to promote the cancer before you finally get the diagnosis of the cancer. But it doesn't mean that this is not a causal risk factor for the disease. It just has to go through multiple steps. Yes? So if it's an indirect step, what would happen is you would not want to control for this, and you would only know that through biology. For the confounder, once you control for this, if it's really just a confounder and not in the pathway, and you'd kind of know something about the biology to make that decision, if you controlled for it, then this association might go away. It would also go away in certain cases if you controlled for this and it was in the pathway. And that's why I said in last week's lecture, you don't want to control for something that's in the pathway of the disease, because that's kind of like over-controlling. You're taking away part of the reason why that leads to disease. So we can think about different types of causal relationships, and I'm just going to go through some examples to show you these categories. It can be a necessary and sufficient relationship. It could be necessary but not sufficient, sufficient but not necessary, or neither sufficient nor necessary. And when I go through the examples, you'll realize that in real life, this is pretty much what we're dealing with. We're not so lucky to have one thing cause disease. So in this, factor A is both necessary and sufficient. If you don't have factor A, no one's going to get disease. And in the presence of the factor, whenever you have factor A, people always get the disease. Can you think of anything that might apply to this kind of a relationship? Yeah.
Radiation.
It could be radiation, although it's not strictly positive that then you will get a disease. It may be a rash, or you'd have to choose something a little less. Yes, yellow.
Not that it's a disease, but sunburn.
Right. If you need sun in order to get that. Yes.
Monogenic diseases like Prader-Willi syndrome.
Right. So it could be like a genetic disease where you're going to end up with this. Yeah. Well, smoking and lung cancer is not always the case, because here it says, in the presence of the factor, disease always exists. There's a lot of people that smoke and they don't get it. Yeah.
Being bitten by an animal with rabies and rabies.
Right. Something like rabies, like exposure to a rabid animal and getting rabies. Is there something else? Yeah. Like HIV to AIDS, you know, the disease doesn't always develop, but you always have the chance, so that's pretty true. And for this, factor A could be almost any bacteria or virus you can think of that then goes on to end up with people getting the disease, if it's a really virulent one where most people get the disease when they're exposed. So here is, each of these factors is necessary, but by itself it can't cause the disease. We need all three of these in order for someone to get the disease. It can't be that you're factor A alone, or factor B alone, or factor C. You really need all three. So it might be that you're exposed to a bacteria, plus you have a depressed immune system, plus, you know, something, you know, you're, I don't know, you forgot to eat for a week or something. So I mean, all three of these have to be present for disease to occur. And then this is, each one of these is sufficient but not necessary. So any of these could cause disease, but it could be factor A or factor B or factor C. Other factors alone can cause the disease. Factor A isn't enough, and this might be something like smoking, where yes, smoking can lead to the disease, but there's other things too that can lead to lung cancer, like say asbestos exposure. You know, and not everyone gets it, but it's potential for this factor to lead to the disease. And really, when we're talking about nutrition and dietary factors and nutrients, this is pretty much what we're looking at, that each factor is neither sufficient nor necessary. It's, you know, unless you're talking about something like vitamin C deficiency and scurvy, you're not going to get that kind of association. You're looking at low intakes of vitamin C plus maybe exposure to someone with a cold, and then you might get a cold. You know, and that's the way we have to think about it. Life isn't pure and simple when we're dealing with nutrition and nutritional epidemiology. We have to realize that there's a lot of other things in the mix that are going to make it hard for us to tease out looking at only our nutrient and our disease. Now, there are ways in the past that people tried to come up with for determining whether or not something caused a disease. And the first criteria were these Henle-Koch postulates, and these were for causation. And this was all on the basis of infectious disease, and this is a long time ago, like before they really knew what organisms existed or how to actually label them. And it was that the organism is always found with the disease, the organism is not found with any other disease, and if you take the organism like smallpox, isolate it from someone who has the disease, and culture, it produces the disease in experimental animals. So this was fine, you know, and you could think of like Mycobacterium tuberculosis. It's always found, that bacteria, when someone has TB, and it makes sense for infectious disease. But as time went on, and remember the first class where I said, you know, in the past, it was all infectious disease. That's what we were worried about. But now that chronic diseases are our concern, we have to move away from this and think of some other criteria. So the criteria that were actually developed for, by the Surgeon General for Smoking and Lung Cancer Association are the Bradford-Hill criteria. And these are still used in legal cases today. People will still use these criteria to try and determine whether or not something caused disease. So they're all listed here: temporality, strength of the association, biologic plausibility, dose response, replication of findings, considering alternate explanations, what happens when you stop the exposure, does the association make sense with everything we know about the exposure and about the disease and how it occurs, and is the association specific? So I'm going to go through each one of these, and this is how I would like you to think when you're going through your papers. You have two papers, so you can think, okay, what's the first thing? Did you have temporality in your papers? Did your exposure precede the disease? And as particularly when we're dealing with things like heart disease and cancer where there's long latency periods, the exposure also needs to precede the latency period. So when we're dealing with chronic disease, a lot of times we need long-term exposure to see whether or not the disease is going to start. Temporality is obviously easier to prove in a prospective cohort design or a randomized controlled trial where you know what the exposure was and it preceded the disease. Another important measure is what is the strength of the association? And depending on your study design, where would you have an odds ratio? What type of study design? Case control and a relative risk. Where can you do that? Cohort or a randomized controlled trial. So when you have stronger associations, they're less likely to be caused by chance or bias. So when the Surgeon General had all the papers on smoking and lung cancer, he had relative risks of about 10. I would be really happy if any study I ever did had relative risks like that. That's really hard to get, especially in dietary exposures. But a strong association means either a very high, if it's a risk factor, or a very low relative risk. So if you're looking at something like vitamin D and fracture prevention, then you would hope that it would be something about 0.3 or 0.4, like the example we had in class. And in general, the stronger the association, the more likely it is to be a causal relationship. So one of the important measures is you're looking at your papers and what was the strength of the association they presented. Another important thing is what is the biologic plausibility? And that means that you know something about your disease to understand if the exposure makes sense in terms of causing the disease. So the proposed mechanism needs to be biologically or etiologically plausible. And when we go through the papers, I've often told you, see here in the results, they're talking about the biologic plausibility, that it makes sense during their discussion that they're saying why this nutrient could lead to this disease. And it should cohere with what we in general know about that disease and that nutrient. And if for some reason your finding isn't consistent with the biology, it doesn't mean it's wrong. We just would hope to see that the finding is replicated, and hopefully we'd have a stronger association, and then people might go back and look at the biology and say, is there something we missed here, a reason why this nutrient might relate to this disease? Another important thing is the dose-response relationship, that changes in exposure are related to changes in risk of disease. It's a strong evidence for causal relationship if it's present, and it also suggests somewhat of a biologic relationship. However, the absence of the dose response doesn't rule out a causal relationship, and that's because for a lot of things like our nutrients, we know that sometimes we have something like a threshold for the nutrients, so that if you think about, we're doing a study, and here we're looking at bone, and this is calcium. Well, if you look here and say this is up to 1,000 milligrams, you might see an association. But if you're somewhere out here and it's above that required amount, you're not going to see an association. So the dose response would depend on, well, what is the intakes we're looking at? If you have 3 intakes here, you'd see a dose response. But if you have 3 intakes up here, you would not. So a dose response is not always required because it doesn't always make sense. But here's one example of dose response. We showed you before for smoking and low birth weight. This is smoking and lung cancer deaths. And you can see that never smoked, the mortality rate per 100,000 person years is 3.4. If you keep going up with more and more smoking, up to more than 2 packs per day, it goes up to 217 deaths per 100,000 person years. So a very strong dose response, a lot more smoking, a lot more deaths. We also see something similar when we look at income and mortality, that this is old dollars, so it doesn't make too much sense with our dollars today, but in general, this is the age-adjusted mortality rate, and remember I told you, if you're looking at mortality rates, you hope that it's always age-adjusted or it might not make sense. And you can see that as income goes up and up, the mortality goes down and down, so showing evidence of a dose-response relationship. Another thing that I alluded to earlier is the replication of findings. The relationships that are demonstrated in multiple studies are more likely to be causal. So if you have 2 papers, they both show the same association and it makes sense, you know, you're more likely to think there's an association there than if you have one paper that shows a positive relationship and the other that shows none. And rarely this isn't required, like I said, that one study where we were looking at DES exposure and vaginal cancer. One of the other things is that you want to consider alternate explanations. Is there some other reason why your association might have led to your outcome? So you would hope that when you're reading your paper that the author kind of says, well, it's possible that we selected the wrong control group, however, X, Y, or Z, that they've considered what impact could other explanations have on this finding and would it hold true. So when we're looking for alternate explanations, we're hoping that we'll come up with a sound study that we can't really think of any residual confounding or bias is existing, and therefore we think it's a true and real finding. So I think let's just take a 10-minute break now, and then we'll come back, we'll finish the lecture, and then you'll go into your groups for your group study for today. So just take a break until 4:30, and then we'll reconvene. Hi.
So the one question on the test, I didn't write, so I don't
Okay.
really care for the point. But that Mike brought up, I think a lot of us were talking about afterwards, and it was similar to one in the book that we got over, that said that cancer is always a rare disease. So since cancer is always a rare disease, like it should be OR and it should be worded the like second way. So it was like brain tumor. So even though it said
I'm
like,
not sure which one you're talking about.
I'm very confused.
It's really bothering me. If we could get started, we still have a bit to do. Okay. So one of the other things that we can use for causal criteria is this concept of cessation of exposure. So if you take the exposure away, do you see the risk of disease declining? And if you do, this provides supporting evidence for a causal relationship. Sometimes, even if you remove the cause, it's not enough. So for example, if someone has emphysema, that doesn't get reversed just because they stop smoking. The progression might be reduced, but the disease doesn't go away. So it's not that it goes away, it's more looking at trends that we might actually see a difference. So this is looking at the years since you stopped smoking and the annual death rate per 1,000 men. So this is the lung cancer annual death rate. And so the more years you go away from stopping smoking, so in other words, this is you just quit, and this is you quit 15 years ago. As you get longer since you stopped smoking, you have a decrease in the lung cancer rate. So that is kind of the trend data that you might show to show cessation of exposure, that you get rid of smoking, and then after a certain amount of time, your risk actually does go down. This is a tryptophan disease. Like basically, we had, this is looking at the number of cases of eosinophilimyalgia syndrome, and this is based on reports to the CDC. So basically, they didn't have too many cases. All of a sudden, they saw this huge jump in the number of cases. And as an epidemiologist, you have to say, okay, well, what's changed? What could potentially be causing this? And what it was tryptophan was on the market. The Food and Drug Administration had approved it back over here. And then when they saw this rise in the rates, they recalled it. And what you see is that once the drug is no longer on the market, that you start seeing a marked decline in the rates again. So that's cessation of exposure to what was the risk factor, the tryptophan, and then you see a drop in the rates of disease. We also, when we're considering whether or not we have a causal relationship, want to think about the consistency with other knowledge or established facts. So if our relationship is causal, we would expect, or at least hope, that whatever we find is consistent with other data. That it's consistent with other epidemiologic studies. If you have like 10 studies, is yours the only one that shows a risk and everyone else shows no association? And also, is it commonly related to the biologic knowledge that we have at that point in time? Some of the caveats is sometimes we find an epidemiologic association without having any idea of the biology of how it occurred. So sometimes it precedes the mechanism understanding. And the other thing is that, remember, we call things facts, but science is constantly evolving. So we might think something is true and a fact at one point in time, but as we learn more, we might kind of revert our thinking or say, you know, now with this evidence, we want to go back on what we thought before. Yes?
Dr. Nieves, is there any sort of like preponderance of evidence or beyond a reasonable doubt standards applied to causality, or is it pretty? I mean, because it sounds sort of vague, or
it is sort of vague, and when you use this stuff in legal trials and things, then they try and get picky and is this true or is this not? But in science, we just kind of say on the basis of what we know. Like, say, for example, smoking. There were a few studies that didn't show smoking and lung cancer association. However, the preponderance of the evidence, most of the studies showed that it was, and the reality is, can people live without smoking? Yes. And so it is, a safer public health thing to say that we believe that there's a relationship here and we're going to take it away. Now if someone came out with a study and they said, the reason why we're having so much osteoarthritis is because people exercise too much, then people would say this goes against the grain of what we believe. And even if there were 3 studies that would show that, people would try and explain it away as confounding or whatever. So you have to like look at the big picture, and it's not like a number, just like I said with a rare disease versus not. It's not like there's a set number. It's just in general, it's a rare disease because it doesn't occur that often. Or in general, most of the evidence points to this, and it would be easy to take away the risk factor, or it would be easy to promote. Like when most of the data showed that if you reduce fat intake, say, you would reduce your rates of cancer. Dahl and Pito wrote this whole book back in the 80s and stuff, and there was a lot of studies that showed that. But as people went on and did more and more studies, they didn't really find the same thing. And part of it is that the study designs got better and better. They went from ecologic studies to cross-sectional to case control, and then finally cohort. And the other thing was that as the knowledge went on and we realized that not all fats are created equal, and we had to separate out, say, the trans fats from the omega-3 fatty acids. So as we gain more knowledge, what we think changes. So it's just kind of, it's almost like a gut reaction. And, you know, you basically, for anything that's going to take an action, it usually requires a committee of sorts. So like the Surgeon General didn't just come out and say smoking causes lung cancer. There was a committee that got together. They reviewed all the evidence. And I'm going to go through some of those criteria in a little bit that are actually used for that kind of purpose. So this is, if you start thinking about the consistency with other knowledge. So if you know that the smoking rates went up, as the smoking rates go up, you get an increase in the lung cancer. So this was the male smoking rates. So they started a lot sooner to go up, and you started to see the rates of lung cancer go up a lot quicker in men, or sooner in men. Women started smoking a little bit later. We didn't really have the right to do so before 1920. That's sarcastic, but so anyway, women started smoking at this point, and then you can see that their rates started going up, and now it's a pretty substantial rate of cancer in women as well. So it kind of made sense. As you see a change in the smoking rates, they go up, the lung cancer rates go up. It makes you think that there is an association. So one of the other things we want to think about is the specificity of the association. Going through these Bradford Hill and that whole list that I gave you, this is another one. So typically it was that specific exposure was associated with only one disease, and that would indicate causality. And that was back with the Henle-Koch, which was really great for infectious disease, but not for chronic disease. So really now the point we're at is that the absence of being specific or specificity doesn't mean there's not a causal relationship. And this is really the weakest of all of the guidelines that we have, because as I showed you before when we talked about causal and factors and, you know, necessary and sufficient, many exposures are linked to multiple diseases. So you have a lot of exposures, a lot of diseases. So like smoking, you have lung disease, heart disease, you have all different types of cancer. So there's a lot of different outcomes. There's a lot of different exposures too. Like it's not only smoking that leads to lung cancer. It could be dietary influences, could be asbestos, it could be other things. So you get to the point where you're just like, okay, well, when is an association causal? There's a few examples where we really feel like we've kind of figured it out. Smoking and lung cancer, high cholesterol with cardiovascular disease, although again, when we got further into time and we realized there's HDL, LDL, and all of that, our hypothesis became a little more specific. Things like tuberculosis, the bacteria leading to tuberculosis, viridans leading to endocarditis, head injury leading to subarachnoid hemorrhage, the graph I showed you, poverty relating to all-cause mortality. There's a few things that we have a feeling about, and this isn't an exhaustive list, it's just to give you an idea. So, and then this is also looking at gastric cancer. And one of the things we learned about gastric cancer is that if you are H. pylori positive, you are at a huge increased risk of getting the disease. If you are H. pylori negative, you basically don't get the disease. And this is something that we didn't always know. It was found out, you know, fairly recently. So this is showing the proportion free of gastric cancer. So you have H. pylori negative just staying right at 1. 100% are free of cancer. If you're H. pylori positive, the more and more follow-up you get, the more and more likely you are to get gastric cancer. So this is another thing that we feel is pretty causal. It makes a lot of sense if you look at all of the data for this association. So let's think about an example. So in 1993, there was a cohort study of laxative use in Alzheimer's disease. The researchers found a significant relative risk. It was 9.5, so pretty strong. It was significant. The confidence interval was 2.3 to 12.8. And this was for developing Alzheimer's disease over a 5-year period. There were 3 other studies that were very similar. One found a significant relative risk of 2.3, and the other 2 found that there was no association. So what do you think? Would you say this is a causal relationship? Just raise your hands if you think it's causal, that laxatives are related to Alzheimer's. Okay, who says it's not? So why are some of the reasons that you think it's not? Yeah.
Not all the studies found an association.
Right, there's a lack of consistency, one of the criteria we look for causality. What else? Yeah.
For lack of better words, it doesn't make as much sense.
So that's like a biologic mechanism, isn't necessarily clear.
I would imagine that older people use laxatives in general to pass stools, and so it could just be the confounding fact that they're older.
Right, so age could be a confounder, and it leads to higher laxative use, and it leads to higher rates of Alzheimer's. So there's a few different reasons why we would think this is not an association. So this is looking at the age of onset of alcohol use and whether or not you go on to have alcohol abuse throughout your lifetime. So there was a study in 1997, and they reported that there was a relationship between the age at the first use of alcohol and the prevalence of lifetime alcohol abuse. And they studied over 27,000 current and former drinkers. And this was the graph of what they found. So here is the prevalence of alcoholism on this curve, and this is based on when you take your first drink. So if you're 13 years old, when you take your first drink, it's up around 45%. If you wait until you're 20, it drops down to about 10%. So do you think that this is an example of a dose response? Anyone have any comments about whether it's a dose response? Yeah.
Not necessarily, because when you start drinking, doesn't necessarily, like, you could start and drink sporadically for 20 years, or you could start drinking heavily at age 10 and do that for the next 20, that'd be drastic, but do that for the next 20 years and have very different effects. So I think sort of dose response would be a more constant.
Right, so there could be an issue with like the quality of what we're really looking at. What does the age at first first time of alcohol use really mean, and is it, consistent use? Is it possible that also there's some kind of a susceptibility, that if people are susceptible to alcohol abuse, they're likely to start drinking earlier? Like you're thinking of cause-effect, but turn them around. Is it possible it goes the other way? So you just have to think through what you're looking at and say, well, what does this really show? If you look at it, the earlier your first drink is, the more likely you are to have a lifetime of alcohol abuse in your future. But it doesn't mean that one causes the other. And you want to think about, well, what are the potential other explanations? And that's what you would hope some of the authors do of, say, the papers you're reading. In the discussion, they might explore alternate hypotheses. What else could be going on here? And that's the kind of way that I'd like you to think. So I'm going to go through an older example just to give you like a historical kind of through the causality pathway. So if we think about the use of estrogen and Alzheimer's disease, there was a case control study, and females that had Alzheimer's disease were less likely than controls without Alzheimer's disease to have taken estrogen. They also did a cohort study by Tang, and they found that the age at onset of Alzheimer's disease was later if the women happened to actually be taking estrogen. And that's shown graphically here, where on this axis it's the proportion of women that are free of Alzheimer's disease. And here's the age at onset, and this is based on the different amount of duration of estrogen use. So if they didn't use hardly any, never, then you're going to be more likely to end up with Alzheimer's disease. If you had more than 1 year of use, more of you remained free of Alzheimer's disease as you go through the different ages. So what we see is that there's a less likely probability of Alzheimer's disease at each age, depending on when, whether or not they had used estrogen in the past. And if we look at this data in a table form, here is the women, the relative risk of Alzheimer's disease associated with estrogen use. So if you did not use estrogen, that's the default. The relative risk is 1. If you used estrogen, then it goes down to 0.4, so like 60% protective with a significant confidence interval. So in this, all of these studies by about 1996 pretty much seemed to show that there was likely a relationship. And then we think about biologic plausibility. Well, someone actually set out to do a study, an experimental study, where they tried to think, well, how could it be that estrogen really could alter the risk of Alzheimer's disease? Is there any truth to estrogen impacting the ability to take neurologic testing? So this was looking at cognitive function. This was Barbara Sherwin did a lot of this work earlier. And so they had people at baseline, and they did their first psychologic test. Then they gave them a drug that basically suppresses their ovaries, takes away their estrogen. And then in some, they gave them back estrogen, and in others, they gave them a placebo, and they did another psychological test, and then did it a little bit further out. So basically, they're saying, okay, if we test the memory here at the baseline, then we take away their natural estrogen, either replace it or don't, what happens to their follow-up cognitive function test? And the results are shown here, where at pretreatment, basically, they were exactly the same, the two groups, whether they were given estrogen or not after taking away ovarian function. At 3 months, you can see that there was a little bit of difference, but by the end of month 5, you can see that the group given estrogen seemed to do much better on this paired association test, which is a test of cognitive function. So the memory seems to be better. So this is pre-doing any drug, giving them the LAD drug, so they do about the same. You give them the drug that takes away their cognitive function, and you can see that they have a drop in cognition. I mean, it takes away their estrogen, their cognition drops. You replace the estrogen, and it goes back up. So you have a couple of things going on here. If you take away the estrogen, you do worse on the test. You give back the estrogen, you do better. So it seems like it made sense. And they went on to think about the biology. Well, what about estrogen could be impacting whether or not someone gets Alzheimer's? So looking at the various biologic pathways, they knew that it stimulates cholinergic markers, increases cerebral blood flow, it acts with nerve growth factors, it reverses glucocorticoid damage, and it prevents neuronal apathy. So on the basis of all of this, they said, okay, it seems like there's an association here. So in the second edition of your textbook, the conclusion they had was basically that all of the data support a protective role for estrogen in relation to Alzheimer's disease, although the picture remains to be completed. So say by like about 2000, this is where we stood. This is about what we thought was the reality of Alzheimer's disease and its relation to estrogen. Then subsequent to that was the Women's Health Initiative, which basically was a randomized controlled trial. So our top level of evidence looking at if we take women and give them estrogen versus placebo, do we see a difference in the rates of Alzheimer's disease or in cognitive function? So this was a study that started in women about age 65 or older, and they found that the drug versus the placebo didn't improve cognitive function. And most women did not experience adverse effects on cognition when taking hormone therapy versus the placebo, but some of the women actually on hormone therapy had a decline in the mini mental status exam, which is another marker of cognitive function. And so there was a little bit concern that we gave the drug to the people thinking it would prevent Alzheimer's disease, and maybe instead we're seeing that there might be a little bit risk. So as time goes on, you have to rethink your knowledge and rethink what is the association. And I think at this point in time, no one would necessarily recommend estrogen to try and prevent Alzheimer's disease based on what we now know. So there's different grades for the research design of individual studies that go through, was it based on a randomized controlled trial? Was it based on a clinical trial that didn't use randomization? Was it from cohort or case-controlled studies that were well-designed and didn't have any problems with it? And this is really the epidemiologic evidence that I would want you to think about. So you can think about how high the evidence is for the different designs, with the randomized controlled trial being the highest. Then we look at the validity of the study, and we're thinking about, well, how good was the study in terms of having any bias or any problems? And that could be good, fair, or poor. And then you look at the overall quality of the evidence, and that's what, looking at all of the studies that are graded this way, do we think that they represent that there is an association between an outcome and the exposure or whatever we're looking at? And so this is what the Preventative Health Services Task Force looks at, and this is what you were asking Chris about, like how good the evidence is, and does it really relate, and when do you say there's a good thing? If you were in a committee, like say the Surgeon General's committee, and deciding, you would be using a grid like this and looking at all the studies and saying, well, what kind of evidence is it? Was there any problem with the study? And then when you have all of these together, you'd say, well, what is the evidence that there is or is not an association? One of the aspects that's kind of just a sideline that's important when we're thinking about causality is the precision, like the degree of the certainty for the estimate of the effect. So it really asks the question about what can decision makers conclude about whether one treatment is inferior, superior, or equivalent to another. And not only do we talk about the strength of the association or that odds ratio or relative risk that you got, but also what is the statistical significance that we got, and what are the confidence intervals for them? Because that's very important too. If I do a study and I have a relative risk of 10 and my confidence interval is 9 to 11, I'm thrilled. If it's 1 to 60, I'm not so thrilled. It means there's a lot of error in that measurement. One other thing is you can look at the grade methodology, where there's 4 broad categories. Like high is that there's a high confidence that the evidence reflects the true effect, and whether or not we do more research, we're unlikely to change our opinion of this. This is not something that people use too often, but this is by Guyot, an epidemiologist, these things. And he basically says insufficient if the evidence is either not available or doesn't really allow us to say what kind of an effect there is between a risk factor and a disease. So I want you to think about, when you're thinking of causality, categorize your evidence by the quality of the study, with the clinical trials being the best, randomized and blinded being the best of those, and then randomized but not blinded, and then non-random. Then we have cohorted case control studies, and then other, which is really our cross-sectional studies, those case reports or case series that we might see. And then I want you to think about causality, and these are the guidelines that you might want to consider when you're thinking about your paper. Some of the major criteria is there a temporal relationship in the papers based on the design that they used for your papers? Is it biologically plausible that the risk factor is related to the disease? Are the results consistent between the 2 papers? And have the authors or you explored any other possible explanations for the finding that they found? Some of the other things you can think about is the dose response or the strength of the association, or if you have any data on what happens when you stop the exposure. So this is just another grid that talks about some of these things that I said. Temporality, just thinking that the cause precedes effect. The strength is that you have basically a large relative risk. dose response, reversibility, consistency, all of these are just defined in this table here. And again, these are the Bradford Hill criteria that are now considered pretty much the standard for looking at causality. And you know, if you have different designs, as you go out through here, you're getting more and more evidence, strong evidence. And as you go out here, you're going evidence against the association. And basically what we're looking for is that we have a temporal sequence, that we have a large effect. These are the kind of things that we want to understand that there really is an association. And the better our trials are in terms of what we're looking at, systematic reviews or randomized controlled trials, depends on how closely we take the evidence to being a real association. So the last thing is just thinking about ethics and, you know, when is there enough evidence to say something is a cause? And would you require less evidence if it's something that's a risk for the population? You're going to take a little less evidence to say what you're going to do. When would we say that something is a cause and actually act on it? Say, have a public health program or make people put labels on alcohol saying that if you drink when you're pregnant, it may cause birth defects. You know, what do we have to say that that could go on a bottle of alcohol? And does first do no harm always apply at the population level? And lastly, are there different guidelines for solutions where we have to do something versus causes where we have to remove something from the environment, like, say, lead and lead-based paint and trying to get rid of it to try and improve cognitive function? What kind of evidence did we need? What did we have to do in order to meet the criteria to get rid of that risk?